Hello, and welcome to our first video on radical reactions in organic chemistry. So this is something that's going to be a little bit different from what we've done before. So I wanted to make sure we have a good solid introduction so it makes sense. So this video is going to be one that's just about how radical reactions work, how they're different, how the mechanisms are going to be different. And then once we have a good foundation with that, we'll go ahead and build on that by doing some reactions in separate videos. A radical species is something that has an unpaired electron. The majority of organic reactions and other reactions in chemistry tend to work with pairs of electrons. So if you think about a covalent bond, that's going to have 2 electrons. If you think about the pi bond, is going to have another 2 electrons, right? So that's 4 total here. Lone pairs have 2 electrons. So usually things are in pairs, and that works well for making octets. But radicals aren't like that. They have single unpaired electrons, so they behave differently. So we said they're going to be very different from the reactions we did before. How are we going to know it's a radical, and what are we going to do with it that's different? So let's talk about that. So what's so special about radicals? So the first thing is, you might notice if you don't know if it's a radical reaction, you might be able to tell because it requires initiation. So there's going to be specific things that show up in the reaction that are going to initiate the radical process. So the 2 traditional types of initiators that you saw in a lot of organic reactions are light and peroxides with heat. So the way we're going to write those is light looks like this, so it's H nu. This may look familiar from Gen Chem, so it's energy equals H nu, so it's quantized energy formula. So that's one option. So there's a specific wavelength of light that's being shot at the reaction that's made to break a certain bond. So we'll see that with halogens usually. The other option is we'll use peroxides and heat. So peroxides are easy bonds to break. It's easy to break the oxygen-oxygen bond. And then once you do that with the heat, that's at a low heat, and then you can do the reaction with the peroxide that you formed. Now, the peroxide usually doesn't matter for a lot of these reactions, so we're just going to put R as in generic peroxide. If you ever see a specific peroxide, that would also be fine. Like if it had 1 carbon or if it had a tert-butyl, those are all fine options. But lots of textbooks write it as just ROOR, so that's how we're going to do it. So now that we've talked about how we're going to recognize a radical reaction, let's talk about what it's actually going to do during the mechanism. So radicals come about because of homolytic cleavage. If you look at the choices are heterolytic or homolytic. Heterolytic is what we've been doing before. So heterolytic cleavage would be uneven splitting. The 2 sides are going to be different when they split. So that would be an example like this, where it comes from an SN1 where the leaving group leaves, right? So we show 1 arrow showing this. All the electrons go to one side, and then you end up with 2 charged items, right? So if you look at homolytic cleavage, it's going to be different because we're going to split each covalent bond that breaks is going to have 1 electron to one side and then 1 electron to the other side. So it's homolytic because they're the same. Both sides are going to be the same when it splits. Lytic means split. Okay, so hopefully that makes sense. You can kind of see them side by side. So we're not going to have charges for radicals usually. We're just going to have the radical itself. So while we're talking about how things split, we definitely want to talk about how the mechanisms are going to look a little bit different from a regular mechanism. So we already said, if you can look, the arrows are going to be different. So we're going to have special arrows. So the special arrows that we're going to have, if you look up here, are going to be one-sided arrows. So they call these a fishhook arrow. If you notice, the end only has one side of a little triangle, like a normal arrow would have 2 sides over here, but then this is different. So it's called a fishhook. It's because it's only moving 1 electron. So a normal arrow, like for example, this SN1, is moving 2 electrons at once. That's how you're going to be able to tell the difference. So 2-arrowed or 1-arrowed. So this is going to move 1 electron. When you're breaking a bond, it's going to look like this. So one's going to go to one side, one's going to go to the other side because the electrons are being split evenly now. You're not moving 2 at a time. If you're making a bond, it's fine now to have 2 electrons come together because even though electrons repel, they also like to be paired. So the energy they're going to gain from forming a bond is going to actually overcome that repulsion. So it's going to work out. So that's what you're going to look for these arrows. They're totally different than the normal arrows that we've been doing where you don't want them to come together. Okay, so hopefully that makes sense so far. So now that we sort of got the basics of radicals, let's see these mechanisms in action. All right, so let's think about radical mechanism steps. So as we've seen before, mechanisms have a pattern, right? There's things that we'll start to recognize that happen a lot of times, like making a better leaving group or like nucleophiles attacking things. So in radical mechanism steps, the process is really defined. So there's always an initiation step, there's usually at least 1 propagation step, and then you can have a termination step. So whenever we're going to talk about those, we sort of need to know that what they are by definition. So the first thing is we'll talk about initiation. So initiation is the thing that's going to start off the radical process. So we have to have this happen for it to work. So we said that's going to be our initiators that we saw previously, right? Like light or peroxide and heat or something like that. So then the point of this is it takes energy to make that happen. So breaking bonds takes energy to work, and then forming bonds usually releases energy. So then you can see if there's a balance between those, which one, if it's going to be exothermic or endothermic, for example. So, but the initiation process is always going to take energy. So we're going to need either that energy in the form of light or that energy in the form of heat for the peroxides or something that's easy to break. So as you can see in the example here, we've got chlorine, and it's going to break apart to form these two chlorine radicals. So if you look at this bond right here, that's actually what's forming the two radicals. The electrons are splitting up into those two. And it's important to know that all initiation reactions are going to follow this pattern. So in the beginning, there's 0 radicals, and then in the end of this step, there's going to be 2 radicals, and there's always going to be 2 curved arrows, the fishhook arrows, that make that happen. So that's initiation. So now let's talk about propagation steps. So propagation steps are different because you've already got a radical. Once you have that radical, it can start reacting with other molecules. Because it's not super stable, that means it's pretty reactive, right? So it's going to come across another molecule, and generally in this example, we'll put an example up, it's going to take a hydrogen. So if we look here, here's the reaction. So I'm going to draw the arrows. So the arrows would be the electrons are going to form a bond and they're going to break a bond. So what's the bond that we're forming? Right? We're going to form this HCl bond. So that's going to be 2 arrows coming together. So one of those arrows comes from the radical itself, and the other one comes from the bond between carbon and hydrogen that we're going to break. So then that's going to be one electron's going to go towards the carbon, and then the other electron's going to go away from the carbon, but we're just going to go ahead and show it going directly to bond with the chlorine. Now, it's okay in this case for radicals. I usually show them as if they're just bonding off in space, and it's fine to show that. It's just easier to see than if you try to smush everything in the corner. But we would understand that the chlorine would actually be, it has to be in proximity to the hydrogen, right? It has to be fairly close. So it would move closer to the hydrogen, and then it would be able to form a bond with it. And then at the same time as that bond's forming, it's breaking the bond between the carbon and the hydrogen. And that's what's going to form our new radical. So if we follow the same kind of patterns we did above, so initiation had 0 to 2 radicals, how many radicals are we starting with for this reaction? Right? Just 1. And then we're going to make how many radicals? Just 1, right? And then how many curved arrows should we have? 3. So we're always going to show 3 curved arrows. Depending on if you're watching a certain video or like occasionally some textbooks, they will not show this final arrow where you're breaking the bond and showing it going to the carbon. But I don't like that because it doesn't keep track of all the arrows and it's very confusing to do that. So we're going to show the arrow that is going to that to make the radical at the end. Okay? So we should also note that when you draw out your mechanism, you're only usually going to draw one initiation step. But propagation steps, you might have multiple of those. So you might have 1 or 2 or 3 of those steps. And then the last thing we're going to talk about is termination. So looking at the steps we have so far, we have one reaction that goes from 0 to 2 radicals. We have one that goes from 1 to 1 radical. So what do you think termination might be? It's natural to expect there to be the opposite of initiation, right? So we're something where we're going to go from 2 radicals to 1 radical. So that might look like this example. So in this example, we know that this chlorine product is something that we get as a byproduct. So one way we could make it is to use a termination reaction. So we'd have 2 radicals come together. So we'll draw the arrows. So one comes from this radical, then the other one comes from this other radical. And then they would go together to form a bond, and then you get the final product. So if we do the same pattern recognition that we did before, so how many radicals are we starting with for this step? 2, right? And then how many are we ending up with? 0. And then how many arrows does it have? 2, right? So it's the complement to the initiation reaction. So an interesting thing about termination steps is they actually happen a lot less often than you think they might. So they sort of wrap everything up in a neat little bow, but they actually don't make sense chemically as much as they do like balancing equation-wise. So if you think about what happens in a regular mechanism, the things that form the reactive species are attracted to each other. So if you have a positive and a negative, they're going to want to go together, right? Because they're attracted. So it's like picking up a paper clip with a magnet, right? Now, if you have a radical, there's no charge. So they're not really attracted to each other. They kind of just go bumping around trying to do whatever they can do. So if you think about it, it would be good energy-wise for those two radicals to come together. That's thermodynamically a good thing. But the problem is the entropy. There's just a lot of randomness that has to occur for them to come together at the right time and place to make this perfect bond. So instead, what they do is they sort of bump around and hit other things. So they might hit the reactants, so more chlorine in this case, and that's actually a good thing. That makes more radicals. We can continue the reaction, but it would occur in a propagation step, not in a termination step. So because this is the more likely scenario for organic chemistry, we're going to always show initiation and propagation steps, and we're not going to show that termination step in our final mechanism. So for my class, you'll see that instead we'll use propagation as the last step of what we show for our mechanisms. So now that we understand the radical mechanism steps, the next thing that you'd want to do is use them for an actual radical reaction. So that's what we're going to do. So we are going to see how we're going to use radicals in a reaction, but I decided it's probably best to make that another video just so we don't get too long. So go ahead and take a quick break and then make sure you watch the next video. So the next video is going to be alkane halogenation. So it's a pretty cool reaction, so I hope you check it out. Thanks. Bye.